Okay, so now when you consider a complex place, you have the contribution of the place is given by a certain function, which in fact is translated, as I explained, by some constant, which is called S sub v. Okay, but I mean, it's rather trivial to treat this constant, so I will concentrate myself on the GC of S. And GC of S was given by 2 pi to the 1 minus S times gamma of S. Okay? Moreover, what interested us was the logarithmic derivative. And this logarithmic derivative is given up to a constant by gamma prime of S over gamma of S. Okay, so what I wanted was to explain the result of André Weil, which was that there is this very nice formula for the explicit formulas. Okay, and this very nice formula is depending on something which is extremely simple, which is that the local factor that you get, namely this gamma prime of S or gamma of S, can be written in a certain universal manner. And this universal manner in this instance is the following, is that again up to constant, you have rho C of S, so which is equal to constant plus the integral from 0, the integral for, let us say, U belongs to C. So this is the local field corresponding to the situation. Modulus of U strictly less than 1. But let me put a decoration on the modulus, okay? I mean, this is the modulus with respect to the complex space C. And then of the expression, which was 1 over the absolute value of 1 minus U, but again with respect to the complex place C. Then absolute of U with respect to C to the power S, and then d star U. So all these things have the usual meaning, namely the modulus with respect to C is given by the action on the R measure. So modulus of Z with respect to C is in fact equal to the absolute value of Z squared, because this is the way the R measure is scaled. Okay? Of course, this doesn't affect this condition, but certainly affects all the other terms here. And the multiplicative R measure is such that when you consider the integral for absolute of U with respect to C less than lambda, okay, of d star U, then this should be equivalent, but in that case equal to log lambda. So I mean, it's readily done, of course, to determine what is this measure, d star U. As we know, it has to be proportional to dz wedge dz bar, absolute value, divided by z squared, okay? But it's better to write it in polar coordinates. And if we write it in polar coordinates, because of this, it's obvious what it should be. Namely, it's obvious that in polar coordinates, if I write z equals rho e to the I theta, d star z then has to be equal to d of rho square over rho square multiplied by d theta divided by 2 pi. The reason for the 2 pi, of course, is that we want the integral in theta to be 1. And the reason for d of rho square over rho square is that we want that this condition, which involves the square of rho, actually gives us a measure du over u on the positive reals. So, I mean, it's sort of obvious. And then if you do the computation, let's do it just to warm up. Okay, so if we do the computation of this integral, as I said, this integral is defined up to an additive constant because as it stands, it's divergent because of the singularity at 1. Okay, and if we just stare at this integral, what is it? Okay, so let's do it. What is it? Well, you see, it is this absolute of 1 minus u. It is the integral of 1 over 1 minus z, but absolute value square, because, okay, I mean, this c absolute value is like this one square. And then what we have is z, then it's to the value 2s, okay? Now, so now I will use polar coordinates. So if you want, my z will be z equals rho to the I theta. Okay, so it will be an integral for rho less than 1. Okay, and it will be an integral over d theta, of course, over all theta. And then I will have to put the corresponding measure here, which is d of rho square over rho square. There is a 1 over 2 pi in front. And then I have d theta, okay? So, I mean, the interesting part is the integral in theta. and it involves 1 over 1 minus rho e to the I theta, okay, multiplied by 1 minus rho e to the minus I theta. Okay? Okay, so you agree with me that if I call e to the I theta, if I call it v, okay, this is v inverse, okay, and when I am integrating on a circle for v of modulus 1, which is what I should do, I have to use the integration measure, which is dv over v, okay, which I have to divide now by 2I pi, okay, if I want to take into account this 2 pi. So in fact, to do the computation, you have to compute the integral over now the oriented circle, okay, positively oriented circle, of this quantity here. But of course, for that, you can just apply the residue theorem, because this quantity is just 1 over 1 minus rho v multiplied by v minus rho. Okay, rho is less than 1, so the only pole is that v equals rho, and the corresponding residue is 1 over 1 minus rho square. Okay, so this integral is obviously equal to 1 over 1 minus rho square. Okay, and now you can change variables to rho square, because it's only rho square which is involved. And you find immediately this, okay, up to sign. Okay, I mean, I'm sorry, you should have told me, I mean, you know, there is a sign mistake here. Okay, because we have a minus here, okay? And it's quite important, remember, this minus sign is very important. It means that we have an overall minus sign when we write the formula, okay, when we fine, so that's okay. And so to recapitulate, if you want, with a little change of variables, what André Weil has proven quite long ago is the following, is that you can rewrite the explicit formulas in the following form, that if you take a function h, so h is a function with suitable regularity properties, say belonging to the Schwarz space of, well, no, it's more than that, it's with compact support, say. Cc infinity of the ideal class group, Ck, and the Fourier transform of H is defined by H hat of chi and z is the integral over Ck of H of u, chi of u, absolute of u to the z, this star u, with the ordinary normalization for the R measure. And the formula is the following, is that H hat of 0 plus H hat of 1 minus the sum of the value of H hat on the Rosen character chi and the zeros rho multiplied by the multiplicity of the 0, n of chi rho. So these are for the zeros of the L function, L of chi rho equals 0, is equal to the sum over places of the field of the integral over the local field k star v of h of u inverse, okay, over absolute of 1 minus u in the local field kv times this star u. Okay? Now, remember how it's done. Simply, I just want to repeat it once more, that the only thing that has to be checked is that, because this formula is sort of additive, provided we keep the same principal values, which was clear from the discussion, I mean, you just have to make the following change of variables to prove it. So you put h of u inverse, okay, equals chi of u times f of absolute of u times absolute of u to the 1/2. Okay? Now, if you take this function, h, what you will find out is that the only place where the only Fourier transform which doesn't vanish is the Fourier transform at chi. And that's because you have the u inverse here. So that when you integrate it over chi, you get a non-zero result. Okay? Moreover, when you compute the Fourier transform of h at chi and z, you find exactly the function psi of z, okay, which was related to the function f, exactly as in the Weil formula. Okay? And then you just follow the Weil proof and everything is fine. All right? So there is no problem. This is done. Okay. Over both. It's both over chi and rho. Okay? You see, for each chi, okay, you have a corresponding sum, but it's also over rho. Now, you see, the functions that we used are functions which only involve finitely many non-zero chi's. Okay? And you can stick to those. You see, if a function is the function being smooth, there would be a sufficient decay in chi that it would be all right, okay? But I mean, really what is going on is a summation over all chi and rho. Okay, so for each chi you sum over rho, and in fact you take the summation over all these. Okay, so that's the Weil formula. And as I said, okay, there is a sort of preferred finite value. At this level, I don't want to discuss it. We shall discuss it later when we shall have a good reason to look at it, okay? At this moment, there is no good reason to look at it. Okay, except, as I said, that we had to have the same for all, but this was clear, okay? I mean, it was clear that whenever I was subtracting constant, I was always subtracting the same constant, because I was, when I made the shift, for instance, I was looking at the difference, and the difference was not singular, okay? It was regular. Okay, very good. So now what I want to do, you know, I mean, I want to look at this formula. I want to get acquainted with this formula and see how it appears from totally different ground. And we already saw a first example, so first case where it appeared, this formula, is the following. So you see, remember, not the last lecture, but the previous lecture, where I was discussing flows and trace formulas for flows. Okay, so let us take now the simplest flow. Let us take the flow which is ft of x is equal to e to the tx. So, I mean, it's an action, so t belongs to R, okay, and x also belongs to R. Okay, so in other words, this flow is acting on the line. Okay, so this is a line, R. And this flow is just scaling. So it has only one fixed point, which is the point 0, obviously. It has no periodic orbits, I mean, but it has one fixed point, which is the point 0. We obviously have that ft of 0 is equal to 0. Okay? So now what we want is we want to apply the trace formula which I had described last Wednesday, okay, to this example. What do we get? There is no periodic orbit. So what do we get? We want to compute a trace, a distribution trace, so that's why I put quote here, of integral of u of t, let us say, times h of t dt, right? Where what is u of t? Well, u of t is the action of the flow on the space, namely, but I want to keep the same notation. Let me see. For the moment, let me not denote it by u of t. Let me just denote it by ft star. Okay? This is better. Okay, so I suppose this is clear what I mean by ft star. Namely that if I have a function xi of x, you see ft star of xi at x will simply be xi of ft of x. Okay, and this is exactly what we were looking at when we were writing the formula for the trace. All right? Okay, so if we write the formula for the trace, and I mean, we do it assuming that h of 0 is equal to 0, namely we don't at this moment look at the transversality issue. Okay, what do we find? We know what we find. We know that this trace, okay, is equal to the sum over periodic orbits, but there is only one. Okay, I mean, it's the fixed point here. Okay, so in fact, it's a sum over 0, if you want. Of what? Then of the integral of the test function that we take, namely here, h of t, okay, which we have to divide by the Jacobian, okay, by 1 minus the Jacobian at the fixed point. Now, what is the Jacobian at the fixed point? Well, you know, the map is linear, so I mean, it is a map itself. So it is e to the t. Okay, so what we have to do is to divide by absolute value of 1 minus e to the t. Okay, and then we have to integrate dt. Why we have to integrate dt? Because we have to integrate over the R measure, which is of covolume 1, on the isotropy. But the isotropy is the group itself, so of course the R measure is the same. So the R measure which is here is the same as the R measure which is there. All right? Now, so what do we get? So let's make a change of variables now. You see, this is not in accord with my notation when I was looking at the action on the Adel class space. Namely, I had defined some representation by u of g acting on xi at x that was equal to xi of g inverse x, if you remember. Okay? So in other words, I had the g inverse in this formula. Okay, so this means that now I have to change my notations simply. Namely, the elements, I have not to call them e to the t or T if you want, but I have to take the multiplicative group. Okay, so this will be an element of R star or R plus star if you want. Okay, so G now belongs to R star. Okay. Yes, or R plus star if you want. And moreover, now when I am integrating, I have to change H to H of U inverse if you want, if I want to stick with this notation here. So what do I obtain as a formula? I obtain that the trace against, again under quotes, of the integral of H of U, U of U. All right, so now I use this notation. This star U, so again this star U is the multiplicative R measure. All right, so that is equal to the integral of H of U inverse, I have to pass to the inverse because of this formula here, okay, divided by absolute of 1 minus U, this star U. Okay? I suppose this is clear. Okay, so we see, if you want, in that example, the first instance where we meet exactly in the simplest possible flow. Okay, we meet exactly the same function as we have in the veil formula. Yeah. Okay, in this local case. So we meet exactly the same function. Now this was for the real line, for R. Okay, and now what we want to prove the same formula, but for any local field. Then the next case now is not when you take the real line acting on itself by multiplication, but when you take the complex numbers, non-zero complex number, acting on themselves, again by multiplication. Okay? So what I want to show now is an extremely simple proof that will not only work for complex numbers acting on themselves, but in fact will work for any local field. Okay? So this will be, if you want, the first very small piece of understanding that we shall get that somehow this veil formula is intimately related to the action of the multiplicative group on the additive group. Yes? No, we shall see a theorem very shortly. I mean, in the second hour, we shall see a theorem, which is actually a theorem, which is a proof. Okay? Okay? I mean, as you say, it is a trace under quotes, but only because it's defined as a distribution. Okay? I mean, it is well defined. It's not, the quotes are not there because it's not well defined. They are there simply because it's a distribution. Okay? Because it's defined as a distribution. That's all. Okay? Now, what we shall see in the second hour, not now certainly, is that we shall have a complete proof of a very precise statement, okay, which will, of course, imply that, but which will be completely precise. And there will be no distribution, no trace as distribution or whatever.
What you want to say that is actually the integral of H of U is so-called quote-unquote trace of U.
No. No, that would be too easy. No. What I am saying is that precisely because of the transversality issue at the origin, the operators involved, even if you smear by H of U, are not trace class. Okay? Their trace only makes sense as in the distribution theoretic framework. Okay? So it's a more serious problem than just the fact that you have to smear the function. I mean, if it was just that you have to smear the function, that would be a very trivial problem. Okay?
When you say that it's a distribution, then you test it on test functions.
No, when I'm saying it's a distribution trace, I am saying the following, which we shall immediately see for local fields now. You see, what I'm saying is the following. You see, we have a certain operator, all right? This operator is integral of, let us say, H of U, U of U, V star U. Okay? And this operator is given by a kernel. So, I mean, this operator, if you want, applied to a certain function psi, and then evaluated at, the whole thing evaluated at x, is equal to the integral of k of xy times psi of y dy. Okay? And now what you want is to integrate over the diagonal. Okay? But that integral over the diagonal makes sense because of distribution theory. It doesn't make sense because of simple function theory. Okay? And that's why it is a trace, not in the ordinary sense. And of course, we shall have to make a little bit of fighting to make it a true trace. But we shall do that, of course. We shall do that in the second hour. Okay? Now, what I want to do for the time is really quite simple.
Definition, where did H and U go?
Sorry?
K.
Oh, K depends on H. Okay?
K depends on
Okay. Well, K, of course, capital U is used to define K.
This is fixed.
Okay? I mean, let's compute k of xy, okay? I mean, k of xy, you see, u of u, as I said, was given by the distribution delta of, if I put the inverse, well, let me change h of u to h of u inverse. This will be a little better. Okay, so let me compute k of xy. So what I claim is that k of xy, in all cases, for any local field. Okay, so now I am not restricting myself to R or C or anything like that. K of xy is always given by the integral. There is an integral because of h of u. Okay, now let me put h of lambda inverse. So let me, u I will call lambda inverse. The reason is that in the formula, remember, there was a u inverse. Okay, and then what do we have? We have delta of y minus lambda x. Okay, the delta distribution of y minus lambda x times this star lambda. Okay, suppose this is clear. This is a kernel k of xy for this operator. Okay, but you see that it involves a delta distribution. So that when now you take the diagonal values, you have to be a little bit careful. Okay, so let me do it very carefully. Okay, let me first do it not carefully, and then I will justify it carefully. Okay, so let me explain what is the non-careful proof for the formula. The non-careful proof is the following. I take k of xx. What is k of xx? Well, it's integral of h of lambda inverse delta of x minus lambda x d star lambda. Okay? I mean, you can't object to that. That's fine. All right? And then, what do I have to do? I have to do integral of k of xx dx. Okay? Now, what is this? You know, this is integral of h of lambda inverse. So far, so good, because there was a h of lambda inverse in the formula. And then I have, again, an integral. Okay, so I put it here. I put delta of x minus lambda x, and I put dx, and I put d star lambda. Okay? Now, look at what happens. Here in this formula, I can make a change of variables. You see? This is delta of 1 minus lambda times x. All right? So I can put y equals 1 minus lambda times x. Okay? Now what happens? Well, then x is equal to y over 1 minus lambda. That's fairly clear. Okay? Now when you make a linear change of variables in the formula for the R measure, by convention, okay, I mean, we know how the R measure transforms. So this will be equal to the integral of, double integral of h of lambda inverse, okay, delta of y, that's perfectly okay, times dy over 1 minus lambda, absolute value, times d star lambda. Okay? But that's very easy to do, because the integral of delta of y dy over 1 minus lambda, that's 1 over 1 minus lambda. So that's equal to integral of h of lambda inverse, 1 over 1 minus lambda, times d star lambda. Okay? So, you see, I mean, this you can take on face value. I mean, that's a perfectly good argument. Now, you see, we shall very slowly progress to make this into a theorem and the rigorous stuff. But the first thing I want to do is to make it rather rigorous relatively. I mean, this is what I had at the start, without a cutoff or anything like that. Still talking about distribution trace formulas, but talking about now arbitrary local fields. You see, I mean, it's clear that when the proof is that simple, you cannot make a mistake somehow. Okay? I mean, at least there is no minus sign or whatever involved. I mean, it's clearly right. So, now, what do you do if you want to justify this? You see, the simplicity of this thing here is that we are not really in a manifold case because it's linear. Okay, when we deal with a single local field. Everything is linear. So we don't need all this fancy stuff about changing coordinates or whatever. Okay, and we don't need, if you want, this micro-localization for making products of distributions, because we don't have to localize first in space and then use Fourier. We can plainly use Fourier. So the idea is the following. Let us use Fourier. Let us use Fourier transform, simply, Fourier transform, in order to define, okay, in order to define, in fact, the product of two distributions, to define and compute the product of two distributions. In fact, that's what we have to do. You see, we are really computing the product of two distributions. Now, what are these two distributions? These two distributions are the kernel k of xy, namely k of xy dy. Remember that in our previous language, this was the delta distribution carried by the graph of the action. Okay? Now what we have to do is to really product this distribution, pull it back by the diagonal, or equivalently make its product by the delta distribution. So we have to make the product of this by delta of x minus y dy. Okay? Sure, but the condition will exactly be that lambda is different from 1. Okay? So now, let's forget about the h, and let's do that pointwise. Because we know that we have really a generalized function. Namely that we can ignore the h, okay, and we can just look at the value. But it will be crucial for that lambda is different from 1. Okay? So let's do it. This is no big deal. Okay. So we just have to understand that when we make the product of two distributions, okay, it is the same thing as making the convolution product of their Fourier transforms. Right? Now here, the convolution product will make perfect good sense. This is what I want to show you. Okay, that the convolution product of the Fourier transform of these two distributions doesn't pose any problem. It is completely straightforward, as long as lambda is different from 1. And it is always this lambda equals 1 which is nagging us. Okay? But as long as lambda is different from 1, there is absolutely no problem. Okay, I mean, and this is mainly a preparation to the second power. I mean, it's really a preparation. So let me start here where this is drying up. Okay, so you see, what do we have to do? As a preliminary step, we should compute a Fourier transform of these things, but we know what is the kernel. Okay, so in fact, we should compute the Fourier transform of delta of y minus lambda x. So what is Fourier of that? Okay, and we also, of course, by the same token, we shall have computed the Fourier transform of delta of x minus y, because it's enough to take lambda equals 1. Okay, so that's the only thing we need to do. Okay, so what are the notations? The notation is that K is a local field now. All right, so it's a locally compact field. And we have the R measure, sorry, we have a basic character. So alpha is a basic character. Well, we need to know, of course, that the local field is its own Pontryagin dual, and that the pairing with this Pontryagin dual is specified by giving a basic character of the field, so that if I take x and y in the field, x is in K, y is in K, the pairing is just given by alpha of xy. Now, the basic character alpha is the following. It's alpha equals, for instance, e to the 2 pi I x for R. It's alpha equals e to the 2 pi I times z plus z bar for C. And it's alpha equals, for periodic numbers, for instance, it's given by the fact that when you divide periodic numbers QP by R, you obtain something which is essentially Q mod Z. Sorry? ZP. R is ZP, sure. It is the maximal compact subring. Okay, if you want, I can call it ZP. Okay? By R, I mean the maximal compact subring also. So, I mean, this is Q mod Z, and you can transform it into roots of unity. Okay, so this is standard normalization, but you can choose any character which is suitable. Now, so this is the pairing between the field and itself. Yes, by the way, when you take a field of positive characteristic, this alpha is really the residue. Okay. Now, so take such a local field and basic character. Now, as I said, we have an isomorphism with the Pontryagin dual. And moreover, what is true also is that, you see, if you consider a K square, for instance, or any vector space, well, the usual rules for changing variables in an integral do apply. So that, for instance, if I consider a linear transformation, you see, if I have d psi d eta, for instance, to perform as an integral, and if I perform a linear transformation L in the integral, then the integral will be affected by the Jacobian of L, but its absolute value taken in the field. Okay? So, I mean, it's really exactly the same formula as we have usually with the absolute value taken in the field. So all these formulas go through. If you want, even the notion of density that I was talking about continues to hold perfectly. Okay? You just have to replace the absolute value, which I was using for real numbers, by this absolute value in a local field. Okay, it's still not yet dry, so I have to do a little more. Okay, so now let me write also a very simple formula of how you compute Fourier transform, how you change variable in Fourier transform. Okay, so let's, for instance, take a function f, and we know it's Fourier transform. So f hat of xi, let us say, but this is it could be in a vector space. Okay, this could be in k square, for instance. So f hat of xi is equal to the integral. I normalize the additive R measure, by the way, dx, so that it is self-dual. Okay? So for instance, when you take this as a basic character of R, it is the usual measure dx, which is self-dual. Okay? So f hat of xi is given by the integral of alpha of xi dot x, f of x, dx. Okay? And I mean, here I am talking about k squared. So x is in k squared, and when I write xi x, I mean xi1 x1 plus xi2 x2. Okay? Now, if you have such a formula, what you can do is you can replace f, for instance, by f composed with a linear transformation. So let f tilde, okay, of x be equal to f composed with a linear transformation. F composed with L of x. I'm just waiting until this is drying up. So. Okay? So, I mean, if you do that, then what you will find out, let's compute the Fourier transform of f tilde. Okay? So the Fourier transform of f tilde at, evaluated at xi, this will be given by the integral of alpha of xi x. Okay? Then I will have f of L of x times dx. Okay, so what do you want to do in order to compute it? Of course, you want to set L of x equals y, and then provided L is invertible, what you have is that x is equal to L inverse of y. Okay, so you see from this formula that you have to transpose L inverse. All right? And you also have to invoke the determinant of L. But what is clear, it doesn't require any computation, is that the Fourier transform f tilde of xi, Fourier transform, okay, is equal simply to the Fourier transform of f evaluated at L inverse transpose of xi, provided, if I don't want to do any computation, the determinant of L is equal to 1. Okay, that's certainly correct. Okay, so let us use that now to compute the Fourier transform of this, or more generally, let's compute the Fourier transform. Okay, so Fourier of delta of ax plus by. Okay, of course, I don't want that a and b vanishes. So I want a be different from 0, 0. Okay? So in order to do that, what do we do? You see, first of all, it's very easy to compute what is the Fourier transform of delta of x alone. Why? Because this is like the delta distribution, delta 0, tensored by the function 1. Okay? When you apply Fourier transform, of course, it passes to tensor products. And so the Fourier transform of that is equal to the tensor product of the Fourier transform of delta 0. But that's a constant function 1 because the R measure is the self-dual R measure. Okay? So this is equal to 1 tensored the Fourier transform of the function 1, and that's again equal to delta 0. So this is equal to 1 tensored delta 0. So what does it mean? It means that if I take delta of x, okay, the Fourier transform is just equal to delta of y, or delta of eta if you want. If you want to keep different notations for the variables xi, eta, and xy. Okay? So now if we apply to delta of ax plus by, what do? We just take a matrix A, B, C, D, okay, of determinant 1, so with AD minus BC is equal to 1, all right? And we just apply the previous rule. So what do we have? If you want, the function we are handling is really f of x equals delta of x, okay? And the linear transformation is L given by the matrix A, B, C, D. Okay? So if we compute L inverse, we have that L inverse is given by the matrix D, minus B, minus C, and A. Okay? Now if we look at L inverse transpose is given by the matrix D, minus B, minus C, and A. You see, let's check. You see, you are right. This is inverse transpose. I'm sorry. You're right. This is inverse transpose, and this is just inverse. Okay. Yeah. Yeah. No, I didn't make a mistake. No. Huh? It's good as it is. Okay. So this is an inverse transpose. And now what we have to do simply is to take delta of eta, okay, and compose it with an inverse transpose. Now, so what we get is simply delta of minus b psi plus a eta. Okay? Okay, so if you want, what we get is that the Fourier transform of this is equal to delta of minus b psi plus a eta. I shouldn't make a mistake, so I think this is sort of obvious. Huh? Okay, so you see I'm just applying this to the second vector.
It's not true if b is equal to delta is of homogeneity degree negative 1, right?
Well, it should be true.
Delta of ax is 1 over a delta of x, right?
No, but remember that you have two variables. Be careful. You see, it's delta times 1. It's not delta of x.
Oh.
Okay? You see? No, do the computation. So you can do it, okay? And you'll see that it's correct. Okay? You see, because you are forgetting the 1. And in fact, the 1 gets transformed in the other one. All right? Okay? So this formula is correct, okay? I mean, of course, you have to watch me, but I think it's correct. I mean, there always exists a C and D, so that AD minus BC is equal to 1, and they don't play a role. So, I mean, it has to be homogeneous like that. Fine? All right, so now let's apply it to what we had. Now, in what we had y minus lambda x, or minus lambda x. I mean, you can, of course, it's this delta of y minus lambda x is equal to delta of lambda x minus y. I mean, that's the same thing. Okay? Because delta of minus x is equal to delta of x. That's no problem. Okay, so I mean, this means that a is equal to lambda, and b is equal to minus 1. So when I transform, I get simply delta of psi plus lambda eta. Okay? All right? And if I apply it for lambda equals 1, I get delta of psi plus eta. Fine? So what are these? These are distributions now on the dual group, namely on k squared. What are these distributions? Okay, so what is this first distribution? Let me call it mu1 or mu lambda. And this one I will call mu1. Okay? These are two distributions. In fact, they are obviously measures. Okay? So let's compute mu lambda applied to a function. So mu lambda applied to a function f is equal, this is an exercise in pedantism, but okay, I have to do it. So mu lambda of f is equal to the integral of f of psi eta multiplied by delta of psi plus lambda eta, okay, d psi d eta. That's the definition of this distribution, okay? But now you see what you can do, because, of course, in this integral you can change variables to eta and say psi plus lambda eta. When you do that, there will be a Jacobian. But as I explained, because this Jacobian is upper triangular, okay, it will have determinant 1. So in fact, you can change variables to that. And if you change variables to that, you see that when you will integrate over, so if you want, I can rewrite this as integral of f of psi eta, delta of psi plus lambda eta, times d of psi plus lambda eta, d of eta. Okay? But when you do the integral in this variable, this means that you fix psi to be minus lambda eta. So what is this equal to? It's obviously equal now to the integral of f of minus lambda eta and eta times d eta. All right? So you see what is going on. We have a perfectly well-defined measure. It is a measure which is carried by the line, okay, given by the minus lambda eta and eta. And if we take lambda equals 1, we have another measure, okay, which is carried by the... Yeah, that's fine. Right, because I am going to justify it, so it's okay. Okay, so what we have is, in fact, two measures. They are positive measures, perfectly well defined, okay? And they are carried, because lambda is different from 1, they are carried by different lines, by independent lines, okay? Now, because they are carried by independent lines, what it means is that their convolution, you see, so I don't know, I mean, for lambda equals 1, it's psi equals minus eta, so it's this one. And for lambda different from 1, it's some line like this. Okay, so now we have to do the convolution of these two measures. So what is the convolution of two measures? Well, what you do is you take a function f, and you integrate the function applied to the sum of the vectors. So I don't know what notations to use, say alpha plus beta. Alpha plus beta. So the alpha and beta are now two vectors, both of them. And then you put d mu lambda of alpha, okay, d mu 1 of beta. Okay, this is by definition the convolution, okay, of the two measures. That's a measure when you apply it to f, to a function f. Okay, so what does it give us here? We just take a function, and we have to add the vectors alpha and beta. So alpha is carried here, and beta is carried here. Okay? But what do you see? You see that, because the lines are different, there are very few choices. I mean, in fact, there is only one choice, of course, which are the corresponding coordinates, to write an element in the form alpha plus beta in the plane. And this is why the convolution makes sense. Okay? If the lines would be identical, I mean, the vectors would be dependent, and you would have, of course, infinitely many choices to write this. So, I mean, then it would be divergent. And this is why you cannot do the square of delta distribution, for instance. But here, the product makes perfectly good sense. So you can compute it. I mean, what is it? So it's integral of f. So let me parameterize the alpha by the eta. So let me see what it will be. It will be like minus lambda eta minus eta 1. Okay, I put eta 1 for the notation for the other one. And then it will be eta plus eta 1. Okay, and it will be the integral d eta 1. Okay, that's clear. That this is exactly the convolution of the two measures. Okay, I suppose there is no ambiguity there. What I have done simply is to write down what are the measures. Now, if you write this integral, it's obviously proportional to the integral of f of psi 1 of f of psi 1 psi 2 d psi 1 d psi 2. Okay, and to understand how, you just have to make the change of variables. Okay, that tells you that the psi, this will be psi 1. Okay, and this will be psi 2. Is it clear? I mean, there will be a Jacobian. I will have to put the Jacobian. So, I mean, let me put some constant here. Fine. Okay, so what will be this Jacobian? I mean, the transformation is the following. It's given by the matrix minus lambda, minus 1, and then 1 and 1. Okay? So its determinant is equal to 1 minus lambda. Okay? So it's, the absolute value of its Jacobian is 1 minus lambda. And because I know that it has to be degenerate when lambda is equal to 1, it's of course in denominator. Okay? So I mean, this is equal to 1 over 1 minus lambda times this. Okay? What does it mean? It means that the convolution of these two measures is a constant. It's everywhere constant in the plane. Okay? And this constant is equal to 1 over 1 minus lambda. Okay? I mean, this is clear. Now, what do we have to do? We have to integrate the product of the distributions. So we have to integrate, okay, the product of the distribution delta of y minus lambda x, and times delta of xy, delta of x minus y, dx dy. But what does it mean to integrate in dx dy? In Fourier, it means to evaluate the function at 0, of course. So in fact, what we are doing is simply evaluating the convolution of these two measures at the point 0, and it gives us on the nose 1 over 1 minus lambda. Okay? So you see that you don't have to think here. It's perfectly justified. It is the same justification as it was a justification in the case of R when you make products of distributions. It is a correct justification when you take C, but when you take C, it will not give you 1 over 1 minus z is the ordinary modulus, but it's the ordinary modulus square, okay, because it will give you the module in the field. Moreover, this justification goes over to any local field, okay? Fine. So, I mean, that's a very simple, quite simple thing, but of course it doesn't touch at all the problem of the transversality at the point 1, which is a crucial problem. Okay. However, it tells you a lot of nice things. I mean, it tells you that you see you have this sort of obvious positivity and so on. Namely, the distributions that you are looking at are positive. Okay, they are measures and so on. So that's a very nice fact, actually. Okay. So in fact, now I will state, and I will prove in the second hour, a theorem which really goes much, much further than that, but which is still in the case of local fields. And however, it will be now complete proof if you want. And there will be no distributions. The problem when you have this trace is defined in this distribution theory is that, you see, they are well defined, but if you want to prove that they are equal to ordinary traces, then you have a lot of work to do. Okay, I mean, this is the usual story. And remember, for instance, if you look at the proof by Atier and Bott of the Lefschetz formula, or by Gilman, Sternberg, and so on, I mean, one has to use something which is a little bit roundabout and families and so on in order to justify the fact that it's equal to an ordinary trace. Okay, so maybe I stop and I will state the theorem at the beginning. Okay, so let me now state the precise result, which is no longer distribution theoretic, okay, but where we are still in the local case. Okay, so in other words, we are in the local case, which means that K is a local field. All right, and you see, what we want to understand is we want to understand the following operator, which is U of H equals the integral of H of U of U, D star U, usual normalization for the multiplicative R measure, so integral over K star, where U of U applied to psi at X is equal to psi of U inverse X. Right? Now, as I said, we want to understand now the problem of the transversality at the origin, namely we no longer want to assume that the function H vanishes at 1, and we really want to compute a true trace. Okay. So to do that, we have to introduce a cutoff, exactly as in the Zellberg trace formula. And the reason why we need to introduce a cutoff is twofold. In fact, whereas in the case of the Zellberg trace formula, it's only onefold. So the reason is twofold. You see, the reason is that when you look at the action of the field on itself, okay, as we saw, there is this fixed point 0. But now this field is infinite in two different ways. Because on the one hand, it is infinite in space, okay? And that is called, the corresponding cutoff will be called an infrared cutoff. Now, why is it called an infrared cutoff? What is the origin of the terminology? I mean, this is exactly what was happening in the Zellberg trace formula. It's called infrared because when you consider wavelengths which correspond to infrared regions, okay, these wavelengths are so long that eventually you cannot say what is a wavelength, which is much bigger than the size that you are considering. Okay, so I mean essentially what you want to remove all the wavelengths which are bigger than what you are considering here. Now there is another cutoff which is very essential and which is called the ultraviolet cutoff. And this ultraviolet cutoff corresponds to the opposite. Namely, it corresponds to the fact that the Fourier space is infinite, all right? And in other words, that now you have wavelengths, or if you want frequencies rather, which are bigger than whatever frequency you are actually being able to observe. And you have to throw them away.
The first would be called infrared.
Yeah, this is what I said. The first is called infrared cutoff, and the second is called ultraviolet cutoff. Okay? And these two cutoffs are essential. Now, it's very easy to do an infrared cutoff. What do? You take a lambda here, say on the real numbers, and you throw away the part of the real line which is outside minus lambda lambda. So in fact, you introduce a projector p lambda, okay, which is such that p lambda of psi evaluated at the point x is equal to psi of x, okay, when the norm of x is less or equal than lambda, and which is equal to 0 when the norm of x is strictly bigger than lambda. Okay, and of course this holds for any local field. If you were doing it for complex numbers, of course, you would cut off outside the disk, and so on and so forth. Now, how do you do the ultraviolet cutoff? Well, you of course make use of Fourier. Namely, you define another projection operator, which is simply the Fourier transform of P lambda, namely the composition of Fourier with P lambda and Fourier inverse. Now, whether you put Fourier inverse here or doesn't matter at all, because the Fourier transform is not quite its inverse, okay? But I mean, modulo the sign of functions, it is its own inverse, and that won't make any difference here, okay? So these are the two cutoff projections. But notice that the Fourier transform P lambda does depend upon the choice of Fourier transform. As you know, the Fourier transform depends upon the choice of a basic character, alpha, and another basic character is related to the first one you started with by a scale. Now, this rescaling will rescale the momentum cutoffs that you are doing. In other words, if you think about the symplectic plane, okay, the size that you are using in the momentum variable depends on the normalization. Okay, depends if you want on the symplectic volume, which is given, symplectic area, which is given. Okay, so now what is the theorem? So the theorem is the following. The theorem is that, so of course, the cutoff operator will be R lambda, which is P lambda at times P lambda. It turns out that if you take them in different order, there is absolutely no difference. And the theorem is the following, is that, so let K be a local field, let H be a cutoff, be such a function, sorry, with suitable regularity. So let's H belonging to CC infinity, let us say, of K cross, of the multiplicative group. Then, okay, for any lambda, the following operator is trace class now. It's perfectly well defined. So the following operator is trace class. So there is no fancy trace with distribution and so on. Namely, the operator which is R lambda times U of H. Okay? And moreover, you have the following. You have that the trace, the true trace, ordinary trace, of R lambda times U of H, okay, is equal to, as in the Zellberg trace formula, a logarithmic divergency, which is 2 times log lambda times H of 1. So this is very similar to when you look at the Zellberg trace formula, plus the integral over K cross of H of U inverse, so the previous formula, divided by absolute of 1 minus U, multiplied by D star U. But now I have to put a prime here, because this integral will even make sense when the function does not vanish at 1, and it will be a preferred principal value, okay, which, as we shall check later, is exactly the principal value of André, okay, in this formula, which was invoking the Euler constant and log 2 pi and so on. Okay, so how is this defined correctly? So you see, this is well defined if H of 1 is equal to 0, because then there is no ambiguity in the integral. So I have to tell you what is the definition when H of 1 is not equal to 0. So where prime means that one pairs, so we shall have to know what we pair, one pairs with the unique distribution, which agrees with du over 1 minus u at u different from 1, okay, and whose Fourier transform and whose Fourier vanishes at 1.
So is this the same as the regularization of 1 minus u to some power or something?
It's not, because when you regularize by 1 minus u to some power, you'll pick an additional Euler constant and log 2 pi in the formula. I will explain that. But this one is dictated, you see, by this theorem. And it turns out to coincide with exactly the Veil thing. But the Veil thing was ad hoc. I mean, the paper by this guy makes it not ad hoc, I presume. I didn't look at it. Yeah, by Bernal. But I mean, anyway, here, from this formula, you get something which is dictated to you. You have no choice. Okay, I mean, I cannot add a constant to this. Okay, you see, I mean, I cannot add a constant. Sorry, I should have said plus little o of 1. In fact, this little o of 1, sorry, is in fact a big O of lambda to the minus n for any n. Okay, I mean, there are no additional terms. Moreover, I am a little bit sloppy when I write 2 log lambda here. When I deal with fields of positive characteristic, or sorry, with p fields, I have to write log prime lambda, where 2 log prime lambda is the integral for absolute of u less or equal than lambda of d star u. Remember that this was only equivalent to log lambda. You see, it is obvious that R lambda, when I take a field whose module is formed of powers of q, it is obvious that the left-hand side doesn't change when I move lambda not among a power of q. So of course this side shouldn't change either, otherwise it would fluctuate. Okay, so I mean this is the log prime. What I mean by 2 log prime lambda is this integral. Okay, I mean that's a very, very trivial point. I mean otherwise if you want you can put lambda to vary only in the module of the field, then it's fine. Okay, then it's correct. Okay, fine. So I suppose the statement is clear, and we shall see that the principal value is imposed upon us by the proof. So let's make the proof of this statement. And as I say, the proof will be mainly an application of the idea of pseudo-differential operators. Okay, whereas the proof in the case of finitely many places will be an idea of an application of the idea of Fourier integral operators. Okay, so let me explain the proof. So you see, now we really have to look carefully. Now we have to look carefully at the previous kernel which I had written here. So remember that the kernel k of xy of our operator, namely of u of h. So this is for u of h. Okay, I had written some formula before. Now that formula was k of xy dy was the integral. There was an h of lambda inverse. Okay, and then there was a delta of y minus lambda x. Okay, and then there was d star lambda. Okay, that's clear. Now remember that, so we choose, okay, so we choose a basic character and so on. So let dx be the self-dual R measure. Self-dual R measure on K. Additive R measure. Yes, yeah, it's just a kernel, yeah. Okay, so this is k of xy. Now let dx be the self-dual R measure on K. Okay, then whenever I have a kernel, you see, like k of xy, I want to think of it like a micro-localized. So what I want to do, I want to introduce a corresponding symbol. So I will define the corresponding symbol like this: sigma of x, I fix x and xi. It will be the Fourier transform. So with respect to, so it will be the Fourier transform. So I don't have to put a normalization constant. I put the basic character. Okay, I put u xi because I Fourier transform with respect to the. I want to have xi here. Okay, and then I put simply k of x and x plus u du. You see what I am doing here? I am making a partial Fourier transform in the kernel so that I can think of it really as a symbol of a pseudo-differential operator. So I am freezing x and I am looking at it as a convolution operator for frozen x. Okay? That makes perfectly good sense. It is the usual thing. So this will hold for any kernel, but I can apply it in particular to this kernel. So let's compute what it gives, the symbol for this kernel. So it will be equal to the integral of alpha of u xi. And then I will have k. Now, k will also be an integral, so there will be an h of lambda inverse. Then there will be delta of, so the x remains the same, but the y is replaced by x plus u. So it's x plus u minus lambda x. Okay, and then it is du and d star lambda. Okay, I mean the order of integration is irrelevant. Okay, so now I have to perform this integral. Okay, but I mean it is sort of clear that when I do the integral over du, Okay, because the u appears transversally in the delta function. Okay, the effect of this integration over u is simply to fix u to be equal to lambda minus 1 times x. So in fact, this integral fixes u equals lambda minus 1 times x. Okay? But there remains, of course, the integral in d star lambda, so that in fact the symbol of this operator as absolute differential symbol is given by sigma of x psi is equal to the integral of alpha of, now u is fixed, it is equal to lambda minus 1 times x times psi, okay, multiplied by h of lambda inverse, okay, and multiplied by, now I would like to write d lambda over lambda, but this is wrong, because if I take the self-dual R measures, there is no reason that the normalized multiplicative R measure is d lambda over lambda. Okay, in fact, I have to divide by rho, okay, where rho is determined by the condition that if I take the integral for x smaller than lambda and bigger than 1 of d lambda over lambda, this is equivalent to rho times log lambda. Okay? Okay? I suppose this is clear. So what I am saying here is simply that d star lambda is equal to rho inverse times d lambda over lambda. Let me write it here. Okay? Because you see, what will be strangest in this proof is that this rho will disappear and then reappear in the end. Okay? This is what is very, very, very strange. All right, so let me write this. So the rho is normalized by d star lambda equals rho inverse times d lambda over absolute of lambda. Okay, and I want to keep also another thing. So now we are almost through with the computation of this symbol. Okay? Why? Because you see here appearing a Fourier transform, but now in the lambda variable. Okay? You see, in other words, my function h was compactly supported on the multiplicative group, but I can extend it by 0 elsewhere. It is still a function. Okay? Still perfectly well defined now. And now I can call a new function. Okay, and this function will be such that g of, let me see, I would like that g of lambda minus 1, yes, is equal to h of lambda inverse over absolute of lambda. Okay, so let me write this here. So I will define a new function by the equality that g of lambda minus 1 is equal to h of lambda inverse over absolute of lambda. So don't worry about the fact that lambda inverse might fail to exist, because then you are outside the support of h, so it's 0. And don't worry about the fact that 1 over lambda might fail to exist, because precisely, once again, h vanishes at this point. So this function is perfectly well defined, okay, function g. Now we can rewrite the symbol, so I will just put it here. We can rewrite the symbol of sigma of the operator. So if you want the operator t, which is u of h, as symbol, this is what we have so far, a symbol which is given by the following: sigma of x and psi is in fact equal to what? Well, there is a 1 over rho.
This is the third time that you used rho today.
That doesn't matter, okay? I mean, I will use it many other times, but it will be the same one. Okay, so I mean, it's 1 over rho times what? Times the Fourier transform, because now I have been able to write this as g of lambda inverse, of lambda minus 1, okay?
What's your alpha, the additive character?
Sorry?
Alpha is your additive character?
Alpha is the basic additive character, okay? Okay?
Yeah.
Okay, for the Fourier transform. So, I mean, here now I have g of lambda minus 1, I have d lambda, but of course d lambda is also d of lambda minus 1.
Right.
Okay? So, I mean, since I integrate over lambda, it's not seen. Right. And in fact, I am just talking about the Fourier transform of g evaluated at x psi. Right. Okay? So, in fact, this symbol is just 1 over rho times the Fourier transform of g evaluated at x psi. Okay? So far so good. That's what we know. Now we have to compute another symbol. You see, here I just computed the symbol of this operator, which was our operator t, which is u of h. Okay? So that was for t equals u of h. But in fact, we need to evaluate the trace of a product, namely the trace of r lambda times t. Okay? So that trace, I will apply the Parseval identity to compute it, and I will compute it at first by the kernels, but then on the kernels I apply the Parseval identity. So you see, R lambda has also some kernel. Let me denote it by R, not rho, but little r, okay? So it has a kernel which is R of xy, okay? Now it's better, by the way, to look at the kernel of the transpose of R lambda, because then I won't mix the x and y, okay? Oh, R lambda is trace class because it's the product of the two cutoffs, okay?
Chopping off.
It's chopping off both in space and in Fourier. So now you have a finite region in phase space, and it's trace class, okay? So now, R of xy, you see, I would rather write it as R of yx, if you pardon me for that, okay? So in other words, R is the kernel for the transpose of R lambda. Okay? In fact, if you do the computation, it doesn't matter, but okay? It is a kernel for the transpose of R lambda. Okay? And now, what is the trace of this product? Well, by the Hilbert-Schmidt property, the trace of this product is in fact equal to the integral of R of xy, now I put it xy, times k of xy, okay, dx dy. Okay, this is just the Hilbert-Schmidt computation of the inner product. And there is no bar, I mean, there is nothing. But in this, I can perform the Fourier transform with respect to not the y variable, but the y minus x variable. So I can set y equals x plus u. Okay. Yes. No, they don't commute.
But you said that they commute.
No. I said the traces are the same. I didn't say they commute. They will commute. I mean, p lambda and p lambda hat will commute for local fields, which are non-Archimedean. Okay. For lambda large, but not for small lambda. Okay. So now I do Fourier transform in y, in u. I apply the Parseval identity, and this is clearly equal to the integral of sigma 1 of x psi times sigma of x psi. Okay, where sigma 1 of x, or rather sigma lambda if you want, of x psi, this is the Fourier transform of R, namely it is integral of R of x and x plus u alpha of u psi du. Okay? Okay, I mean this is just the Parseval identity. Okay, so now let's compute, because it's so simple, the Fourier transform of R. Okay? After all, what is R? I mean, it's done on purpose. You see, the transpose of R, but as I said, I mean, this wouldn't matter. The transpose of R is not just a product in the other order. Okay? So that R of xy is easy to compute. R of xy is given by, so again, I will use rho, I'm sorry. Okay? So but it will be rho lambda. So rho lambda is a cutoff. Okay? Rho lambda is this function, which is 1 for x less than lambda and 0 elsewhere. Okay? So it will be rho lambda of x, of course, because, okay, I multiply this side. And then it is the Fourier transform of rho lambda evaluated on y minus x. Okay? I mean, this is clear. It's clear that the kernel giving you the operator p lambda hat is convolution kernel, which is the Fourier transform of the cutoff function. Okay? So it's also clear now that if I Fourier transform, so if I write integral of R of x plus u, alpha of u psi du, I mean, it's obvious, okay, that this Fourier transform now, which is sigma 1, is simply equal to rho lambda of x times rho lambda of xi. I mean, you know, there is nothing there. Okay? I mean, this is just tautological. I have just written twice the same thing. So, I mean, this now is our sigma lambda of x and xi. Okay? So now we know what integral we have to perform. It's obvious. We have to perform the integral in the x and xi variable of the product of these two symbols. Okay? But remember that the first symbol is so simple. It's just the product of these two cutoff functions. So in fact, the integral is just truncated now. We don't have to write rho lambda of x and rho lambda of xi. We just have to write the truncated integral. Okay? So let me find a clean place to write it. This is not yet dry, so let me write it perhaps here. So in fact, you see the trace of R lambda times u of h is given on the nose by a double integral, okay, where x in absolute value is less or equal than lambda, and xi in absolute value is less or equal than lambda, okay, of what? Of the symbol sigma of x xi, which, as we know, is equal to 1 over rho times the Fourier transform of the function g, evaluated at x xi Okay? And the integral is dx dxi. There is no other normalization because the Parseval identity is on the nose because the R measures were self-dual. Okay? So this is what we have to compute. That's all. Let's compute it. Now we shall make a change of variables. So I need to say a few words about changing variables in local fields. Okay? Because after all, it's not differential forms. Okay? So, but however, you see, my change of variables will be the following. I will let the new variables be x and x psi. Okay?
It is differential forms. You call them gauge forms or something?
Right, if you want. Okay, but I mean, I just want to say that there is a formula without using any fancy stuff, which I will justify in 2 lines. Okay? Yes?
So here is the psi lambda multiplied with psi.
Sigma lambda.
Yeah, sigma lambda multiplied with sigma.
Yes.
That you have only one.
Because the sigma lambda, the role of the sigma lambda was just to cut off the integral.
Oh, okay. Yeah.
It just chops off the integral. Okay?
That's the integration.
Okay. So let me just mention in 2 words what I am saying here. You see, I call this new variable u. Okay? Now the mapping x psi goes to xu has a singularity, obviously. Okay? However, from the point of view of measure theory, the singularity is measure 0. And you have the following formula for integration, which I will write here. So there is a formula which allows you to replace an integral, which is just, in fact, an obvious formula, which allows you to replace an integral in x psi by an integral in x u. Okay? So what is this formula? You see, if I have to integrate a function of x psi dx dxi, which is what we have to do, okay, then what can I do? I mean, I can fix x and apply Fubini, okay? I mean, and then I can change variable from psi to u for fixed x. But if I change variable from psi to u, I will introduce dx du over absolute of x, okay? I mean, this is clear. And I will just have to change my function accordingly. So this should be obvious, okay? Now we have to care also about the domain of integration. What does this domain of integration becomes when we change variables? Okay, this is the first thing we have to care for. So the x less than lambda doesn't change. Okay. Now if I want to recover psi from x and u, okay, what do I get? I get that psi is equal to u over x. Okay. So the condition that psi is less than lambda means that the norm of u over x is less or equal than lambda. Okay? And that means exactly that the norm of x is bigger or equal to the norm of u divided by lambda. Okay? Now you can ask me what happens at 0. All right? Now there are 2 issues to see. The first issue is that you will not get all u's. You will only get those u's for which norm of u is less than lambda square. Okay? So this is the first point, that norm of u will be restricted by norm of u smaller or equal than lambda square. Okay? And the second issue is that when x is equal to 0, but this is a set of measure 0, okay, you would normally have a problem. All right? So we shall have to be careful that our integrals are convergent near x equals 0, that everything can be done in absolute value. Okay? But what do we get now? You see, we get a formula for changing variables, which is that if we take such a function, we can write this integral as an integral of f of x, and psi now is equal to, as I said, u over x, okay, times dx over x, times du. Okay? So this is what we are after. Now, in our case, of course, the function is particularly nice, but so what do we get? We get that the integral we are looking for, okay, so the trace of r lambda times u of h, okay, it's equal to what? It's equal to the integral for absolute of u inferior or equal to lambda square. Okay, now what was the condition on x? The condition on absolute of x was that u, absolute of u over lambda, is less than or equal to absolute of x, less or equal to lambda. Okay? Okay, I'm just, it's just, if you look at the log of the modules, it's just a linear transformation that I'm doing. So I am just, This is very simple. Okay, and what is the function that we're integrating? The function f of x and xi was equal to 1 over rho g hat of x xi. So this is 1 over rho times g hat, but x xi is equal to u. Okay? And then what do we have? We have dx over x, and then we have du. Is that okay? All right? So of course the integral in x drops out. Okay? And what do we get? We get the integral for absolute of u less or equal to lambda square. Okay? Then we have to understand what is the integral. So now I can write over there. The integral of, so 1 over rho, so this is where the rho will disappear, but it will reappear later. So 1 over rho integral, okay, for modulus of u over lambda less or equal to x, less or equal to lambda, okay, of what? Of, I must have somewhere dx over x, okay? Now, I claim that this is equal on the nose to 2 log prime lambda, okay, and this is where the nuance with the prime enters, minus log of absolute of u. Okay? I mean, I suppose you believe me for the real line, or for but I mean, and the rho is very important, because remember that the 1 over rho times the x over x is a d star x. But it has already been shifted into inside another integral, okay, this rho. No, it's log u. Okay, let me go through that. That's very important, you see. Because anyway, u belongs to the powers of q, absolute of u. Okay? Whereas you have to put the prime here because lambda does not belong. Okay? That's the reason. You see? I mean, you see, the point of the prime is the following, is that you have an interval, let me be very specific. You have an interval which is like minus log lambda to log lambda. Okay? And you have powers of q. If you count how many powers of q, you see, you will have one more because of the endpoints. That's why I put the prime. Okay? But if you subtract the u, you will not change the situation of endpoints. Okay? So it will be exactly log u. Okay? That clear? I mean, of course you have to be extra careful with these little points, but I mean, it checks correctly. All right, so now we know what we are computing. We know what we are computing. And what do we get now? See, we have... okay, so what do we have? So the integral is just equal to trace of r lambda times u of h equals, so now I can replace by its value, and what do I get? I get integral of 2 log prime lambda minus log of absolute of u, and it's again for u less or equal than lambda square, times g hat of u du. Okay? Fine. Okay. Okay, so let us treat the two terms independently, but let me first observe that because the function g is a function in short space, the Fourier transform of g hat decays faster than any inverse polynomial. Okay? And in particular, the log prime lambda is beaten by this. Namely, if I consider the integral of, for instance, g hat of u in absolute value, okay, for u bigger or equal to lambda square, okay, this integral here. This du is a big O of lambda to the minus n for any n. Okay? Okay? That's in particular that thing down there. Okay? This will be infinitely harder when we deal with finitely many places. Here it's a triviality. Okay? So, I mean, here I am just using the fact that I have a nice function. Okay? And that I can just do that. Well, in fact, I don't need that it is an order of lambda minus n, but it's a short function, so it goes to 0. Okay? I mean, it's certainly little o of 1. And you don't need anything to prove that. Okay, so anyway, we have this. So this means that, let me see. In fact, the same would hold if I would put log u also here. Okay? Because, I mean, log u is a polynomial, really. okay, with respect to the module. It's really the simplest polynomial. Okay, so this continues to hold for log u. And so this means that now I can replace modulo a little o of 1, this integral which was only for u less than lambda square, by the full integral. Okay, so that's equivalent if you want. Well, equivalent is not the right word. I mean, it is equal to little o of 1 plus, okay, the integral for all values of u now of 2 log prime lambda minus log of absolute of u times g hat of u du. Okay? Very good. So what do we know now? Let's consider the two terms separately. Okay? Now, the term 2 log prime lambda times g hat of u du is absolutely no problem. I apply the Parseval Fourier inverse if you want. And what do I get? Of course, I get g of 0. But what is g of 0? Okay, I mean, obviously, g of 0 is equal to h of 1. Okay? So we do get a multiple of h of 1, which is 2 log prime lambda. Okay? Okay, now we have to be much more careful, and we have to look at the other term. So what is the other term? The other term is obtained as the integral of minus log of absolute of u. First of all, notice that the integral is convergent at the origin, because the log of absolute of u is integrable near the origin. So we don't have any problem with Fubini or whatever. Okay? So all the previous argument is justified because of this integrability, local integrability of log u. Okay? And now what we have to do, we have to understand what is the Fourier transform of the distribution minus log u. Okay? And I claim it is exactly the Veil distribution properly normalized. That's what I claim. Okay? So let me prove that. So now what we need to understand really is the Fourier transform of minus log u. I mean, the sign is very important. So. And don't forget that in some way or another, the rho which has disappeared must reappear. Because in our integral, we had a d star u, okay, in the Veil formula. Okay, so we have to be able to find it again somewhere. Okay, so let's do that. Now, so the lemma is the following. The lemma, let me write the lemma. The little lemma is the following. The lemma is that, the following. That, so let, again, K be a local field and so on. Then I claim that I will consider a certain distribution, which is the following. I will define a certain distribution P by P of f equals the limit when epsilon goes to 0 of the integral of f of x d star x. So d star x is our normalized multiplicative R measure, okay, for norm of x bigger than epsilon, so bigger or equal, okay, plus log of epsilon times f of 0, okay, and epsilon, say, varies in the module of the local field.
What is the principal value?
This is the principal value, okay. This is just some choice of principal value, which is particularly agreeable. It's not the right one, but it's particularly agreeable, this one, for the computations, okay. So the lemma then contains the following statement. The first statement, A, is that if I take P, well, first of all, P is well defined, okay, as we shall see. If you apply P to a translated function, Fa, to a shifted function, sorry, by scale, okay? So this is f of a, Fa of x is equal to f of ax, okay? So if I apply this to this function, what we shall see is that it's equal to P of f minus log of absolute of a times f of 0, okay? I mean, this should be very clear. And then the second thing, B, is that if we take the Fourier transform of P, okay, so P hat of vector psi is equal to, or vector u, let us say, is equal to minus log of absolute of u plus constant. Okay? Now, it will follow immediately from this lemma that, okay, we shall be at home. Okay. You see, I mean, in my talk in the colloquium, I was talking about this symbol, integral. Now, this symbol is precisely the study of this distribution, log u and of the corresponding thing. Okay, so I mean, all these things are very standard but quite important. Now, so let us check everything. Now, you see, first of all, this limit makes sense because if you take the function to be constant, okay, and if you look at this integral, say it takes the characteristic function of the maximal compact subring, for instance, okay, in a non-Archimedean local field, then this integral here will just be equal or equivalent to log over epsilon, okay? I mean, log of 1 over epsilon because it's a positive number. So when you add log of epsilon, you get something which is finite. So this limit exists, okay, certainly. Moreover, if you replace f by fa, what happens is that here now you have f of ax. I mean, d star x doesn't change, okay? But if you put ax equals y, then the condition which was here is now replaced by that y is bigger than this, okay? So normally you should have subtracted log of epsilon times a, which you didn't. That's why you get this difference here, okay? Now, if you look at the Fourier transform, p hat of this thing, and if you write down in Fourier transform, if you transport this equality here, okay, you will obtain a certain corresponding equality for p hat. This equality will be that p hat of ax is equal to p hat of x minus log a. Okay? Why? Because the Fourier transform of the Dirac mass at the origin is the constant function equal to 1. Okay? So in fact, from this, you immediately know that the Fourier transform has to be equal to minus. The minus is very important, okay? Because this function is positive near the origin, okay? And so it has to be equal to this plus constant, okay? Now, the constant is what determines your choice of principal value, all right? Now, in our case, we know we want the constant to be 0, okay? That determines an additive multiple of the Dirac mass at the origin, which has to be added to this, okay? If you take that principal value, the constant won't be 0, okay? So, but what do we know, in any case? What we know is that the integral of minus log u times g hat of u du, we know we can now rewrite it, minus log of absolute of u times g hat of u du by the Plancherel formula, okay, is equal to the integral of g of x, okay, times a certain distribution, which, remember that I was here using exactly this star x. It's because you have this star x that you have exactly the log, okay? So now I can put again here my rho, and I can put 1 over rho, okay, times, and it's again the 1 over rho. I have to keep the 1 over rho. You will see that it will again shift to another place. Okay, so 1 over rho times dx over x. And let me put a prime here, because we take a very specific principal value. All right? Now let's replace g by its value. Remember that what we had is that g of lambda minus 1. So, you see, so remember this formula now. Okay? Remember this formula, that g of lambda minus 1 is equal to h of lambda minus 1 over lambda. So now I better change my x, put x equals lambda minus 1. Then it will be very easy to compute. So this is equal to integral of g of lambda minus 1 times 1 over rho times d lambda over absolute of 1 minus lambda. Okay? Okay? Now what is g of lambda minus 1? It is equal to h of lambda inverse, okay, over absolute of lambda. And this is what I was saying about the rho. You see? Now I assemble 1 over rho d lambda and absolute of lambda, and I call that d star of lambda. And I get exactly the desired formula, that this is the integral of h of lambda inverse, okay, over 1 minus lambda times d star of lambda. But you see that the prime is rather subtle, okay, because the normalization for the prime was coming at another place, okay, namely it was mixing the additive and the multiplicative, okay. Now it is an exercise. Sorry. Yes.
You put the prime there.
I put the prime.
Yeah.
Now I ask you to check, but I think in fact. Okay, I ask you to check. I did in the paper with much straightforward computation, and I love these straightforward computations. Okay, that this integral prime is in fact exactly the Veil factors. Okay, namely it accounts for the logs of 2 pi, it accounts for the Euler constant and so on. Okay, I ask you to check it. I don't want to do it because that's boring. It's crucial. It's crucial because if we are going to prove positivity of the Weil distribution, okay, I mean it's absolutely crucial that they are on the nose. So, but I mean this can be checked. This is done in the paper. I don't want to bore you with that.
Can I ask?
Yes, sure.
If you, in the theorem, if you replace it just by one of the truncations rather than the product of the two, you know, the
Yes,
thing,
then it doesn't make sense.
I mean, it's not traceable anymore?
No, it's not traceable. It's
You
not
need the
traceable.
Fourier transform.
You need both. You see, you need, it's exactly like in spectroscopy, you see. In spectroscopy, when you see these absorption spectra, you need to make a cutoff both ultraviolet and infrared. And I mean, this is absolutely crucial. I mean, it's absolutely crucial that, as opposite to the Zellberg trace formula, where you only have the sort of spatial, you see, cutoff. Here you have both cutoffs. I mean, this is absolutely key. Okay, I mean, the fact that you have both cutoffs. And I mean, so as I said, I mean, okay, this is, so this works now. Now we have a perfectly well justified stuff. And so this treats completely the local case. Now, what I want to say in 2 words before we stop is what is now the formal computation in general, and now we shall proceed to make it much more rigorous and not formal. You see, now we have, for the local fields, the perfect statement, okay, for a local field. Operators are trace class, the thing is justified, and so on, and it looks very much like the Zellberg trace formula, okay? Now, let me do the non-perfect statement in the global case, just in a few lines, okay? Remember that in the global case, what do we have? We have the ideal class group, CK. You see, first of all, you see, let me make a very important remark, which is that imagine that you don't know about this ideal class space, and let me explain how you will be forced into it. Okay? You see, so now you say, oh, I am so happy. I have the Weil factors which appear from a local computation. Okay? So immediately now you want to put all places together. And to put all places together, you have only one thing to do, which is to take the ideals, namely, which is some sort of restricted products of the corresponding local field. Okay? Okay? Now imagine that you are doing that, and that you compute the corresponding trace of the action of the ideal group, J, which is, if you want, again, the restricted product, restricted, of the multiplicative groups. I mean, after all, it's a product of the previous situations. Okay? That's what it is. It's restricted, but if you would consider, for instance, finitely many, it would just be a product. But imagine the mess it will be when you take the product of these traces, because the trace of a product is the product of the traces. That's what it is. So what you will find out is that it's a formula which does not involve the sums of the various places, but which involves arbitrary products of these sums. And this is wrong. Okay? I mean, this is not the Weil formula. Okay? Now, the amazing fact, and the fact on which I will insist many, many times, is that this mere operation of dividing by k cross is like taking a primitive part. And in fact, it will end for you a trace formula in which now only these terms will appear additively, one by one. Okay? Now let us see why this is so at a very crude level, an incredibly crude level. That crude level is the following. Consider CK is the ideal class group acting on the ideal class space, namely this space X, which is A mod K cross. Okay? And let us analyze the fixed points. You see? Now there is a quotient map from the ideals to the ideal class space, which I will call pi, and there is a quotient map which I can call C from the group of ideal, okay, to J. Now if you have a fixed point downstairs, this means that you have an equality that an ideal class C of G multiplied by an ideal class pi of A is equal to pi of A. Okay? Now, this means that you have the equality JA is equal to A modulo K cross, so AQ, okay, where Q is an element in K cross. But obviously it means that you can bring this Q here, and you have J tilde times A is equal to A. Okay? Now what does it mean? It means that you have an ideal which, when you multiply by some ideal, is equal to itself. The only way it can occur is that if the ideal has some 0 somewhere, okay, to occur non-trivially. So this implies, if it's non-trivial, that some place there is some vanishing of A sub V, and that the corresponding J sub V then is arbitrary. It belongs to K star V. Okay? Now what happens, and this is at an incredibly crude level, is that this gives you the sort of nice isotropy. They are the only isotropy subgroups which are co-compact subgroups in the ideal class group. And they are exactly the inclusions of the multiplicative local fields in the ideal class groups that you have from class field theory. Okay, these fixed points. Moreover, for each of them, you can very easily understand what is the Poincare return map and the transverse situation. Namely, it is given exactly by the action of K star V on the transversal. Okay, what is a transversal? Because AV is 0, okay, when you move along the orbit. At this point, you do not move 0. So the transversal is exactly KV. Okay, namely the local field KV. So what is the Poincare return map? It is simply the multiplication lambda goes to lambda x, okay? I mean x, sorry, goes to lambda x for x belong to KV, and for lambda belong to the isotropy, which is K star V. Okay? This is the Poincare return map. What is the module of 1 minus the Poincare return map? It's 1 minus lambda. Okay? So what do you get? In a very crude way, and I will explain the many places where I've been sloppy. But what you get, if you want, in a very, very crude way, is that the trace should be the sum over all places, because they all contribute, okay, of the integral of h of u inverse, or lambda inverse, rather, okay, over 1 minus lambda at this extremely crude level, d star lambda. But there is a very nice fact that d star lambda has to be normalized so that it has covolume 1, remember. And that's exactly the normalization which is given by the module, okay? So, I just wanted to give you a glimpse of that, but things are much more difficult than that because, as we shall see, there are many points which have to be clear. But this is the rough presentation, okay, of the global situation. But you can already guess, you can already see that you are forced into this K star. You see, you cannot just work with adels and idels and so on. You would get an impossible mess. Fine.